back. We're live. It's a Monday afternoon. It's 1 o'clock. And we have a special guest who we interviewed in January of this year. It seems like a long time ago, but it was a great talk show. Milton Garces, who's the assistant researcher, and he is the director of the Infrasound Laboratory at the UH facility at NELHA, the Natural Energy Laboratory of Hawaii, Natural Energy Laboratory of Hawaii Authority in Kona. I was a director there for a while.
What?
Yeah, way back when. You were just a young man.
Yeah.
Welcome to the show, Milton.
Thank you, Jay.
Great to have you. And it was great to do that show in January. And one thing sticks in my mind is, I always like to ask scientists what moments they had in their lives that sort of connected them with their science, committed them to their science. And you had an interesting story. You were walking in the woods, and you heard a certain sound. Want to tell that story?
Well, I can tell it forever because every single time you can add another different sound on it, right? And the memories are funny that way. You can keep replaying them. This one was a jungle in Costa Rica. And I was chasing this volcano down. I heard it was really consistent in terms of blowing things. And when I arrived there, I couldn't see anything. It was a jungle. All I can hear is monkeys and thunder, lightning, lots of rain.
A lot of sounds in the jungle.
Lots of sounds. But then when that volcano blew up, it's like, it's the one. There's no ambiguity about it. This thing is there. You could hear rocks rolling down the hills, and you could, it had its own voice. And I realized, hey, we can use this. And so that kind of set me along the path, and it's been a journey of exploration since then. That was like over 20 years ago. And since there, you keep finding all this primitive language that we're tapping into and trying to interpret and decipher. It's a translation exercise, What is this particular signature trying to convey to me that
Lots
is useful?
of unique signatures. Yeah.
There's no end to them. And it's shaped by the environment that you recorded in. If you record it in a valley, it's going to have this reverb going to it. It'll be like a church, here, like a giant temple. And if you're in a desert, it's going to have a different signature because the way that, the heat shapes the sound. And if you're on the hill, it wraps around the hill, so that shapes it too. And how it bounces off, sometimes you can hear the echo of a forest, So to try to extract the voice of the source itself, it can be challenging. But it's tons of fun, really.
Well, this sort of leads me to discuss the title of our show today, which is Infrasound is Everywhere. Okay, we're going to define infrasound, but I thought, talking about your walk through the forest in Costa Rica, we could also call it yes. A tree makes noise when it falls alone in the forest.
Yeah, but so many records of that. So, so solipsism is not going to work out for us on that field. Yeah.
So just to until we could record sounds, we couldn't do any of this. And then we got to record sounds, and I think the magic was we got to look at them as a waveform. And so you have only two things, right? You have the waveform with all the complexities that a waveform can take, and you have the levels, the volume. Is there anything else?
That's a good summary of it. The waveform contains a lot of content, and the relationship between the timing of arrival and the levels also give you that. But those are the primary metrics that you're trying to understand, the amount of energy that goes in there. The other thing that's really critical is the timing.
The timing.
Yeah.
Thank you.
Time is of the essence.
Timing is of the essence.
That's everything, So yeah, we're looking at really low frequency sounds. So the same programs that we have in audio that are so accessible to us because we use it all the time. Yeah. We run them into them, but the scales are just huge. They're massive, from scales of buildings to global. And so, going back to the whole sound is everywhere thing, we found infrasound after Krakatoa blew up,
What is infrasound exactly, relative to waveform and frequency and level, and the sound levels? What is it?
Well, it's everything we define seems to be human-centered. So we define it relative to a hearing threshold. And, guys like us are hearing low end. It's more on the 30 to 40 hertz. But a young person might be able to hear down to 20 cycles per second.
Okay.
Which is, it's like a really heavy bass.
Yeah.
And below that, you lose the sense of tonality. So you no longer get a tone, you start getting more of a beat. And so infrasound is below 20 cycles per second. A lot of what we concentrate on detection for infrasonic signatures, it's around 1 cycle per second.
That's, okay,
So it's a beat.
okay.
You know,
It's a beat, it's not a frequency or a musical.
It's a really slow
sound,
60 beats per minute kind of thing.
Yeah.
And it kind of, if it's smooth, you barely hear it. You don't feel it at all. If it's sharp, then it sounds like a percussion. And then you have 2 cycles per second. That's 120 beats per minute.
Yeah.
And now that's like a swinging jazzy piece right there. That's really
Okay.
rocking, right? 120 beats per minute is happening.
Yeah.
But there's a lot of information in there. It's just slow, and it corresponds to scales that are bigger than us. That's kind of like the reference point. You know, you start getting to elephants, they start producing infrasound. You get to whales, they go into the infrasound range. So the big boys, the big things in the world. And then you get even bigger things, you know, like tsunamis or giant meteors hitting the Earth, and now everything rings. The whole planet is like a giant spherical gong. And so this is when we talk about infrasound, we talk about really big, long
sounds.
Yeah, deep, and they're so loud, it's ridiculous, you know. Yeah. And we just don't feel them. I think we'll go nuts.
Well, why? Because they're outside our hearing.
Well, you know, our ears pretty much dictate the frequencies that we hear.
Yeah.
Because if otherwise, it's just shaking thing, you know. And we use the time of our hour between our ears to know where things are coming
So
from.
humankind has evolved to avoid hearing these sounds because it would be too tough on us.
I think we'll go nuts.
Yeah.
It's so loud down there. There's so much energy
Yeah.
in the infrasound range. And then you go deep enough, you hit weather.
Yeah.
And you know, sometimes when it's really windy, I don't know if it happens to you, but it's unnerving. If it's windy all the time,
Yeah.
and everything's vibrating.
Yeah.
And so I think we just filtered it out, but we still kept some of it because when you hear that, you know, Godzilla, right? You look at the movie, brrr, big sound, right? So they communicate with infrasound, right? In the movie, they're communicating a low
dogs.
Dogs go on the other end because their heads are smaller. So they can go to the ultrasound.
Ultrasound.
So then the bats go to
Infrasound,
ultrasound.
ultrasound.
That's right. It's all relative to us, right? We define it so we get first dibs. And if it's below our hearing threshold and it's big, it's infrasound. If it's above and it's small, it's ultrasound.
Okay. So what are the boundaries then? I mean, for your use of infrasound,
Mm-hmm.
where does it start in terms of cycles per minute or whatever, second, whatever, and where does it end?
It's an arbitrary boundary, really.
Yeah.
There's no, physics doesn't care. The only real boundary between sound and it goes into a different type of wave. It's about 3 millihertz, which is, you know, 0.003 cycles per second. So you get to a few hundreds to thousands of seconds of oscillations. Now sound loses its meaning, so you switch physics there. But above that, it's all sound.
Yeah.
So we design systems just like our ears. We design recording systems that scale with the wavelength. So essentially, is we grab our ear and we throw it in the wall and we throw it to the other wall, and now we can detect sound that's bigger.
Yeah.
And so we design the systems with particular, you know, signatures in mind.
But you know what? It raises an interesting question because you're using infrasound for science.
Yeah.
You're learning about the universe, about everything around us, and there's really no barriers. Once you understand the unique waveform, the unique properties of a given sound, you can test it, you can find it, you can interpret it, anything. But you know, then there's this other range of human sound and dog sound and all this. You haven't even started with that yet. So I mean, when you finish, Milton, when you finish with what you're working on now, there's a world of other sounds for you to work on. It never ends, right?
There's no end, and that's just in this planet. You know, you start thinking about, you know, Venus has got an atmosphere, Mars has an atmosphere. And if you look at things big enough, then, you know, stars and planets become like little molecules in a vast volume, and that whole thing oscillates too.
Yeah.
So there's no limit to scale, time. You can go as small as you want, down to the molecular level, subatomic level. You get phonons.
Subatomic sounds.
Yeah, it's kind of wild. You know, when I went to school, the phonons was like a mythology. They were like unicorns, solid-state unicorns. And now everybody talks about them. There's papers on it, and it looks like they're part of it. But this is, you know, it's a quantum mechanical equivalent of sound. Yeah. And then you can go down to the Big Bang sound.
Really, really, really big, like a universe exploding.
Yeah, you use like Planck reference constants, you know, to
Yeah,
scale
yeah,
things, you
yeah,
know, and
yeah.
then we're still vibrating from that, right? So it really is no limit to it.
But you need different instruments with different kinds of, different parts of the spectrum, so to speak.
That's right.
So what kind of instruments are you focusing on now?
Now I'm building cell phone apps for recording infrasound. This is pretty much, you know, I still remember the first system that we installed. I was so proud of it. It was so beautiful, but it was so expensive.
Yeah.
You know, it was prohibitive. And that, you know, the really nice things just cost a lot of money. And so if you want a high quality, high def, you know, high fidelity equipment, you know, you pay for that. But that limits how well you can capture it.
Yeah, but it's always got to be digital, right?
Always.
It must be digital.
It must be.
Okay.
But now your smartphone is a computer, it's a supercomputer. These things are awesome. They got 24 bits resolution inside of them. The audio interfaces are amazing, you know, because what do we all do? Listen to music to it, right? So high fidelity, high data acquisition rates. Communication is amazing. So now, you know, anybody that has like an iPhone right now can record infrasound. Anybody. You know, just go to the app, download it, press play, and you're not recording infrasound, but contributing it to, you know, to the science.
So there's a microphone.
I know, it's internal.
The microphone picks up the sound.
Yeah, yeah.
And then the microphone goes through some sort of digital processor, and it stamps it in a computer file.
Yeah.
And the computer file has those things, a frequency and waveform and levels and you know, the whole signature is
So
right there.
We don't even connect the microphone to it. We use the onboard sensors in there. But seriously, if you have it right now, you just go to the App Store, type infrasound, download the amps, push play, and you're good. You're contributing. You're recording infrasound. And it's that easy.
I'm going to do that during this break.
Cool.
We're going to have a break. I get my phone.
All right.
Get your phone. Infrasound, okay? That's Milton Garces. He's Associate Researcher, Director of the Infrasound Laboratory at the University of Hawaii in Nelha, the Natural Energy Laboratory of Hawaii Authority in Kona. We'll be right back for more.
Hi, I'm Donna Blanchard. I'm the host of Center Stage here on ThinkTech Hawaii. Center Stage airs every Wednesday at 2 o'clock, and of course you can check out our archives on YouTube or on ThinkTech Hawaii anytime you like. Why should you do that? Because this is an arts show that I believe is making a difference in lives. We talk with artists of various ilk. We talk with painters and writers, playwrights, novelists, poets, sculptors, dancers, you name it, directors, actors, of course. And we don't only talk about what people do, but we talk about how they do it. And my favorite part of the conversation, we talk about why they do it. And it's really common on this show to hear people say, wow, I didn't think about it that way. And it's very common to hear people afterwards who have seen the show say the same thing. And I hear all the time that people are inspired by the conversations that we have. So why don't you join us and be inspired too? That's Center Stage on Wednesdays at 2 o'clock. We'll see you Center Stage.
Okay, we're back, we're live. I learned in the break, I mean, I could find a definition of infrasound.
That's good.
I didn't look at everything, but I found that on my Samsung, it doesn't, the apps don't work on Android yet.
It's only for iPhone, iOS for the moment, but we're going to fix that. You know, we have to test it and something that there's so many Androids. There's so many flavors. You know, it's like walking to a candy shop, Android candy
It really
shop.
is. Okay, so you were talking about how you could spot a satellite.
Yeah, we had this Soviet satellite that came in, you know, a few weeks ago.
Yeah.
And it flew right over Hawaii. And so people saw it. There's some nice footage of people who took the shot. I was like, look at this thing. This thing's flying over. So we had the cell phone app recording on Big Island in Oahu. And we have stations in Maui and Hawaii also. And there it was. By golly, we picked up a decommissioned Soviet satellite burning in through over Hawaii. And that was satisfying. We've already picked up volcanoes, and we already picked up the usual things that blow up. You know, so we know it worked, but that was the first time we catch this big.
Okay, so here's the satellite.
Yeah.
And I have my iPhone.
Yeah.
And I'm pointing it up
Don't
in the
need to.
sky. Don't even need to.
No, if it's just recording, that's good enough.
Just record. And what about recording while you and I are speaking and
Yeah,
having a call, whatever it is?
No matter.
You
Sit in the
can,
background.
you can extract that.
It's so deep,
You're looking at infrasound, so not sounds,
you could
different.
even cross.
Ah,
Our voices are like, in fact, we build the app so it filters out voice. We don't
so
want
you
to.
don't care about the voice.
It's for privacy.
Okay, so now, good, good.
Yes.
See, there is privacy left in the world.
Of course.
In science, yeah. So now I have the sound, the infrasound of the satellite up
Yeah.
there. Now you're gonna do something with that sound file. And so
Mm.
what do you do in order to gain the specific signature of the Russian satellite? You know,
You know, the typical thing is pitch, right? Look at the frequency and find, okay, what is its prevailing voicing, right? And so you concentrate on that. But you always look around the edges, because you never know. And then you try to reconstruct what the trajectory was. And, you know, things that are moving supersonically, they appear to behave acoustically. They don't, but they do, because you see things way before you hear them, because they're moving faster than sound.
yeah.
So you have to think about things right, and they have weird radiation patterns too, like that meteor over Russia, right? That humongous thing that blew out the Chelyabinsk meteor. You heard about that,
Now
right?
you're telling me now.
Okay, I'm telling you now. Okay, so this giant fireball exploded over Russia. And it exploded over ex-nuclear Soviet facility. It used to be a secret facility. And so you can imagine, you know, the stupid.
They got paranoid over that.
You know, you
yeah.
get little twitchy people over there, you know. And so you don't know at first, what the heck is this thing? It's a big fireball. It's the biggest atmospheric explosion we've had since the Cold War, since they banned nuclear weapons. And it was the equivalent of about a 1 megaton nuclear explosion. This was a big rock, and it came out of the sun. We didn't see it coming, so there was,
How far up?
it blew up at around 30 kilometers, but actually hit the ground.
Oh,
We didn't know it hit the ground until we looked at the seismic signatures, and because it fell inside a lake.
which is another signature.
Yeah, so it's all connected, right?
Yeah.
So this thing screams through the air, and freaks everybody out, broke the windows. Nobody died, but you know,
Could have.
if you look at the YouTube Chelyabinsk, you see people freaking out, windows exploding, people running out because they see a light. The light precedes the sound, right? Then this thing slams into them. All the dash cams that are in Russia. And we wrote a Nature paper using essentially YouTube from all the cameras that were parked around there. So this crowd sounds right there using citizen
So
science.
YouTube, somebody posted a video on YouTube, and you could listen to the soundtrack of the video.
We looked at the trajectory in the video channels
Yeah.
to get just the path.
Yeah.
And that is because the dash cams are really popular in Russia
Yeah.
for some reasons. The sound went around the world twice. We picked it up in Russia, in Kazakhstan, then in Europe, then in the equatorial, and then in Antarctica. So wow, this went on. Then it went wrapped around again, and then it wrapped back again. So this was like, this is when we realized this is a big one.
Did you know the unique signature of it, or did you have to figure that out logically?
Well, we get hit by meteors, big ones, like Hiroshima-sized big ones every year. So I mean, this is where water came from. You know, on Earth. It came from space. It got delivered via
Wow.
meteor, right?
Yeah.
So we've been slammed as a planet routinely, but you know, we're 70% water. So these rocks fall in the ocean.
Yeah.
That's it. But the big ones like this don't happen that often. And so we knew more or less what a, 10 kiloton type meteor looked like, as we get once a year. But we weren't too sure what a 1 megaton meteor sounded like, and now we know. Yeah.
So you have that recorded.
We have that
You
recording.
can isolate the exact signature.
It's gorgeous.
Why do you say gorgeous?
Because the signal to noise is just massive. It's like somebody screamed. Our sensors were so good that you captured the whole thing.
Clean.
Oh,
Clean waveform. Yeah.
Clean. It's just so nice. It was picked up 600 kilometers away, and it was like, and then all the way in Antarctica. And then
So this will enable you to know more about the next one.
yeah. Next time it comes, we'll be ready for it. We know what we have a baseline.
When can you pick it up, though? So you say it was, what was it, 60 miles, was it, over the surface?
Well, we moved to the speed of sound. So that's the propagation signal. And then the closest station that we had was Kazakhstan, which is 600 kilometers away, right? And that's when I realized, shoot, anybody with a cell phone could have picked this up. Not just on the microphones, but the barometers too.
Yeah.
You know, seriously, this thing was like, just
So you
massive.
talked about, before the show began, you talked about citizen scientists.
Yeah.
Citizen infrasound scientists.
Yeah.
So you could have people, you know, all around the world recording things. How would that work? I mean, if you had anything you wanted, you know, if you could get everyone to do what you wanted, what would you ask them to do to achieve a library of unique sound files, unique sound files, to give you, you know, incredible information on science? What would you do?
Well, you know, when I go to bed at night, I plug my phone in, connect it to the Wi-Fi, and then if you can just push record, it's being powered, it's on a communication line, and it's recording, it's contributing, and everybody has to sleep. That's 8 hours of continuous recording anywhere in the world. So while you sleep, you're contributing to science.
Where is it recording? On the phone or?
Yeah, on the phone. It's just using the phone as a communication device that captures sound and streams it to the server. So it'll be like the SETI guys, right? SETI guys, who, you know, they look for extraterrestrial intelligence by using crowdsourcing it, right?
This reminds me of a very strange file that was on Apple phones a few years ago, and it recorded your GPS location right down to the, you know, inch, wherever you were on a file. So every second or two, it would record this in a file. And when somebody found the file hacking the iPhone, you know, it went to Apple, and they said, what is that? How come the GPS locations, you know, every second or two on the phone, and you're recording them? Are you removing that from my phone? Are you taking that off my phone? What's the purpose of it? It's not helping me. And Apple declined to answer that.
Interesting, yeah.
Well, they stonewalled the question. And so, but theoretically though, you could have the phone recording all the time.
Yeah.
And it doesn't take much. And you could have it filtered so nobody, you know, wasn't eavesdropping or anything. It's just we're talking about infrasound only, and you could have it there. And then theoretically, you could have it, you know, batch that back to you at Nelha. You would have so much data, you wouldn't know what to do with it.
It's a problem.
And you would know what to do with it.
We're thinking about what to do with them, but the potential is like incredible because, again, everybody's got a smartphone, just about, even in the most remote parts of the planet. So we could really increase the density of coverage of planetary scales by factors of like 10,000, really. It's and what you describe is exactly it. You know, it's running in the background. We built the app on purpose to pretty much preserve privacy. We randomize the ID, the location you can volunteer out of that. And I don't know, I got here by putting your address on Google.
Of course.
Right? And then this little voice tells me where to go.
Yeah.
And he knows where I am. I don't mind volunteering that. I do it on purpose and willingly because then I get here.
Do you need GPS in these files?
It helps.
It helps.
It helps.
Then you can triangulate that way.
That's right. You can use network processing, the time of flight thing, you know.
Yeah.
Where are you and where the source is, and you can backtrack it.
Yeah.
And for Hawaii, one application is for surf. Big waves create big sound.
Oh, sure.
Any surfer knows this, man. Dead of night, I hear this rumbling, and I was like, oh boy, showtime tomorrow.
So you know, when you look at these sound files, you know immediately, you can screen them out. This is a wave, this is a volcano, this is a plane, this is a satellite, this is a Big Bang, whatever it is. And you don't have to worry about them being confused, right? It's so unique, am I right?
There is some unique signatures, and again, it depends on the recording environment. The problem is that I can't do it all. So I have to train a little computer somewhere to do it for me at very large scales. And that's the beauty of it. That's when you start going into like machine learning, and you use all these resources that are like available everywhere now. So it's a new world order now. We have beautiful digital signals coming in from all over the planet. And we have the resources and essentially unlimited computing power. When you think about it, we can compute just about anything we can imagine. Yeah. And it's there already.
Okay, so let's talk. Let's say you want to know about wave action in the ocean. Yeah. I mean, I don't know if it's on. I got to look at all your things you're doing. You're doing so many things. Okay. But let's say it's wave action in the ocean. So I get all these, all the sounds coming in from, I don't know, the ships at sea, the people live on the ocean, people live inland. You know, I don't know, everybody. What do you do with them? I mean, how do you process them, and what do you do with the result?
So usually we are event-driven. Most people don't care about something until it affects them directly. So say, for example, you're sitting peacefully in your, in your villa somewhere on vacation, and the volcano next door blows up. You just happen to be there. All of a sudden, you become very interested in that thing, right?
You bet.
That's when you turn it on. You say, oh, wait a minute, I would like to know more about this, and if everybody did that, we'll have full coverage of that activity live. And then the idea is to build an interface that you can go and answer your own questions. So what happened? Thunderstorm over this region. Where is it at? So in principle, you should be able to just find out yourself. It's a search engine, right?
Yeah.
A signature signal search engine that you can do yourself. Because there's no way I can do it all. I cannot satiate your curiosity. It's not possible. But you can do it yourself.
Yeah. What would I use to do it myself?
Oh, we'll build a web page interface. You can just log on and
See it.
see it.
See the visual representation.
And query it. And
Well-
interrogate it and find out, okay, how about this? How about that? And just play until
Like,
you
give me an
happy.
example of a question.
For example, let's see. Let's pick something topical. Oh, yeah. Let's say you are in a volcano, right? And you hear this loud rumble. And you're kind of worried because, you're pretty much sleeping next to a volcano. And you want to find out what's going on around here. So you probably go to Hawaii Volcano Observatory, right? And you go find out, okay, what's the prognosis there? What is the average? And that's the best place to go, to a government agency. And you can also just start recording and then look around and find out who else has signatures around there and find out what else is happening in the area. And part of the idea is to make this available at a level that is accessible, but not worrisome, right?
Yeah.
So you feel better informed, and it ties into all the available feeds that can inform you in real time about what's going on around you. So it's a way of enhancing situational awareness, right? That's the key word. What's going on around me now? And when you feel in a position of when you're threatened, this is when all your senses go up. It's a way of expanding your senses beyond your limitations.
But okay, suppose we have
Yeah.
a tsunami sound.
Right.
Ooh, okay, and then you have an algorithm that will determine how far away it is, how big it is, all that. So you press the record button, and now it's hearing that signature and it's hearing the approach, and it's smart enough to know that it's a tsunami and it's approaching. That's pretty terrifying to an ordinary fellow living on the beach.
That's right. So what you will do is take this data and not try to interpret it yourself, but provide it to the people who can.
Like you.
Myself or the Pacific Tsunami Warning Center in this case, right? Because you have your own sensor, you understand that, maybe you know where you are, but you have to put it all together. And that's more difficult. And so, yeah, for example, for the Japanese tsunami, we had a huge infrasound signal that arrived here 5 hours before the tsunami did.
Yeah.
But we didn't know that could happen. So
Yeah.
to those like a aha moment, we could potentially use this. And for the last Chile event, we didn't pick up any infrasound here in Hawaii. Fortunately, we didn't get much of a wave, but still.
Yeah.
It's somewhere in South America, there is a signature of that event.
Yeah.
We don't have access to it. The trick is to give it to the people who can use it, and you as a citizen can help with that.
Yeah.
You see, to make that available to the agencies that can
And
provide
then
that
the agency
information.
will do the processing
Yeah.
and tell you what it means
Yes.
and give public advice
That's
as
their job.
necessary.
Otherwise, it's terrifying, like you said. Because
Terrifying.
The responsibilities you
Theoretically, you could do that.
It's very difficult to do it because of
You need a big
it's
computer.
our limits of comprehension, really. We have cognition limits as humans, as individuals, right? We almost need like something bigger than us to really comprehend what's coming at us at that scale.
Yeah.
And this is why there are organizations who do this, because
yeah.
they can put it all together and then let you know, hey, it's not a good time to run, right?
Talking about the future, you're talking about applications that we can't even imagine yet.
Oh, we're
that will
imagining
connect
this.
us.
Yeah.
And after this break, I want to get to some of them, what you're doing and what you will be doing as time goes by.
Sure.
This could be a long career, actually, Milton.
I hope so. It's fun.
Milton Garces, Associate Researcher, Director of Infrasound Laboratory at the University of Hawaii in NELHA, the Natural Energy Laboratory of Hawaii Authority in Kona. So we're talking about infrasound. And our title is Infrasound is Everywhere. And yes, a tree does make noise falling alone in the forest. We'll be right back.
Aloha, I'm Kili'i Akina, president of the Grassroot Institute and host on Ehana Kako, a weekly program on the ThinkTech Hawaii broadcast network. Ehana Kako means let's work together. Think of the sad alternative, let's not work together. Here in Hawaii, with all of our diversity and the richness of the people, it's important for us to come together around issues on the basis of what's right and what's good and what's going to serve the common good. And that's what we try to do at Ehana Kako. Every week, we interview movers and shakers, people in government, business, and other sectors of society to talk about how to create together a better government, economy, a better world here in Hawaii that can bless the rest of the world. I thank you for your attention to ThinkTech Hawaii, and we look forward to seeing you every Monday, 2 to 3 p.m. on the ThinkTech Hawaii Broadcast Network. We're Ehana Kako, and we wish you well. Aloha.
Okay, we're back. We're live. We're having a really good time today in science. This is like Mr. Science, this one. That's Milton Garces, Associate Researcher and Director of the Infrasound Laboratory at the University of Hawaii. We've learned that there's sound everywhere. The trees do make noise falling along in the forest, and we can learn from that. We can process from that. We can learn about our world, and it's only beginning. It's only beginning how much we can do with this. So we actually found the app on the iPhone. We'll be showing you that in a little while. But for now, I like to take stock of your projects where you're learning about this and actually doing it. And I have a little list. The infrasonic radiation from the winter surf season on the North Shore. Talk about that.
Mm-hmm. Yeah, when we first discovered surf infrasound, it's the nice thing about being so niche. You specialize in something that you find new stuff all the time. So we found out direct association between the intensity of a wave breaking and the infrasonic signature. And we actually put some sensors on the North Shore. And we found that that pipeline is just dominating in terms of surf infrasound. I think whenever there's a west swell, it just goes. And that thing just rings like it breaks so hard that the majority of the infrasound comes from there. But with different directions, different surf spots turn on. You have sunset turning on with more of a steep north swell, and so.
So this means that the different surf spots will have different signatures.
Yeah.
You could identify one surf spot against another with the signature.
Yeah.
And furthermore, let me ask you this one. This is interesting. Every single wave theoretically has a different signature. Is this possible?
Yeah.
Oh, wow.
Yeah. And it's distributed, right? Because, it's not just one point, but it's...
Yeah, across the wave.
But talk about a complicated conversation, right?
Yeah.
But yeah, each wave has, and sometimes they're similar to each other. Because as every surfer knows, this is what's attractive about some surf spots. They have the same kind of wave, but they do vary between different points, which makes sense.
You could evaluate a surf spot.
You can tell how hard it's breaking.
Yeah, and you could tell them you should go out or maybe not.
Pretty much. That's how big it is, especially at dead of night, because you can't see. And it's really hard. I mean, how many times have I stared out there? I can't tell how big it is.
Yeah. Oh, interesting.
Oh, no.
Okay, so then you had another one, real-time acoustic monitoring of eruptions in Kilauea.
This is a collaboration with the Hawaii Volcano Observatories. And again, they're the primary authority for anything volcanic on the islands of Hawaii. And essentially, we provide additional information as needed. If something changes and they're interested, they queue, and then they have access to the data. And in collaboration with them, we've also built a network on the Big Island. So we have really nice reception of pretty much anything that happens there. And the aim is to provide coverage not just for Kilauea, but also for Mauna Loa, which, as you know, just changed its cloak to yellow.
Yeah.
So it's not if, it's but when Mauna Loa is going to erupt, and when it does, we'll be ready for it.
Yeah. Okay, and so this leads me to another question I always have. So if the Earth, through these eruptions, is giving you infrasound, and you can find a signature on it and tell us a lot about what's happening or what will happen, what about when there's no eruption? Does the Earth make sounds between eruptions when nothing is erupting?
I guess Kilauea has been erupting continuously for a long time. And when we first made the measurements, they told us, this volcano is quiescent. It doesn't make any sound. Oh, we went and tested them anywhere because there's no better place to test a system than to throw it at a volcano. Because if the volcano doesn't kill it, the fumes will and something else. So you test for robustness.
Yeah. Get validation.
Field test, like a real acid test, literally, right?
Okay.
And that's when we discovered, we wrote the first paper, that volcano infrasound from Kilauea volcano. It's like, oh, not only is it making sound between major eruptions, which is all the time, it's just gurgling away.
Yeah.
And sometimes it's really very tonal. You have all these conduits and pipes and stuff, and it sounds really pretty sometimes. It sounds like a
different
chant,
volcanoes have different signatures.
Very, very different, yeah. Kilauea is nice, but there's some of the nastier volcanoes, the ones that inject ash into the stratosphere.
Yeah.
And this was another great aha moment for it. This is the acoustic fingerprints of a Plinian eruption. And those are the ones that most people care a lot, in particular here in Hawaii, because almost everybody flies here, right? And planes just don't like ash. Planes ash bad, right? So anytime a volcano pumps ash into the stratosphere or into the flight paths, there's a problem. And so we have a project now starting in Asia for Indonesia, Philippines, and other big bad boys out there.
To listen to the volcanoes.
Using the global network and starting to also deploy the cell phones around there.
And then you can tell if it's going to be the eruption and therefore the ash.
And who to inform and what are the communication
If you
paths.
change the flight plan.
You have to. Not only that, sometimes that costs money because you have to drop off passengers so you can put more fuel.
Yeah.
Right?
Yeah.
So there's an economic impact.
So wreck the engines with the ash, too.
And that's a big cost.
Yeah,
and
yeah.
the worst case scenario is the thing falls out of the sky.
Yeah.
And that's just bad all around.
Yeah,
Right?
yeah.
But so there's a whole decision chain that follows an eruption alert, as we found out in Iceland, right? There's people stranded, people were very cautious, nobody flew, and it pretty much multi-billion dollar impact in economic damage from that eruption.
So we had a scientist a week or two ago here who taught me from HIGP, Hawaii Institute of Geophysics and Planetology. Are you associated with them?
Very much so.
Are you part of?
Red Butler's my boss.
Okay, got it.
And
All
he
right.
told me, hey, you have to go talk to Jay. And I said, it
got
would be my pleasure.
All right, what else? What else? Of course. So I want to say his name is Jeff Anderson. He was here a couple of weeks ago. A great guy, great discussion. And one of the things he taught me was that the Earth is a magnet.
Mm-hmm.
And I was a magnet fellow. It's a magnet fellow, studies magnetism. And the Earth is a magnet, and it has a kind of molten core. And the molten core obviously is moving around. Mm-hmm. And therefore, it's kind of like a volcano, I suppose. Mm-hmm. And because it's moving around kind of like a volcano, theoretically, don't you think that it should be giving off sound, infrasound?
Well, that's an avenue I've never considered because there's all this solid rock in between.
There's too much material.
But do you want to hear something weird? That same magnetic field, right? It's the only thing that keeps the sun from scorching us. This is our shield. This is the only thing that prevents all this cosmic radiation from essentially.
It bends the radiation away.
Yeah,
from us.
it provides a cover, essentially.
What a great idea! Whoever invented that.
Yeah, pretty cool design, isn't it?
Yeah, smart. Yeah.
Yeah. This is well done, right? And with the big event there, the Japanese earthquake and tsunami, we found these waves propagating on the lower edge of that boundary. Now, we never thought there were infrasound waves there because there's no atmosphere there to speak of. But there is a high density of electrons there. And apparently they move like sound. So we found infrasound in space. It's out there. And the physics of that is really complicated because you have a plasma out there. So it doesn't behave like your typical fluid. And then you have wave equation, then you have electromagnetic equations. And it gets really complicated because we think of the sun as this happy thing that's just staying there all the time, but that thing's changing. The storms that are going off up there. I don't know if you've seen some of those images out there with the big jets that come out of there. And every time something like that happens, we just get a pulse. And so that shield that we just talked about is not static. I think that can make sense.
You could interpret that.
And not me personally yet, because I'm just learning about it. But I think there's something in there that could be very intriguing. The physics are fascinating, and just learning about that is such a lifelong student kind of thing.
Yeah. No, that's incredible to think about it. And I guess the question is, I mean, we know that knowing about a tsunami is useful. We know that knowing about waves is probably useful. We know that eruptions are useful. But there's probably other uses that infrasound could give you, aside from those ocean and earth movements.
Mm-hmm.
Have you gone in that direction? Can you talk about how it will give us other information that will help humanity?
One of the primary applications that we have is for the Comprehensive Nuclear Test Ban Treaty, which is we monitor for clandestine nuclear test explosions in the world. And before the turn of the century, the field of infrasound was gone. There was nothing there. So we had to reboot it. It was like a full, restart of it, which was nice.
15 years ago.
Yeah. So there really, the field was just gone. There's only like maybe 5 people doing this in the planet. And then we signed up to do nuclear test explosion monitoring for the Comprehensive Nuclear Test Ban Treaty, and we built the global network. And that's when we started discovering stuff. Because before that, we were working on paper, like strip records, smoke paper kind of stuff like that. So a little limited dynamic range.
Very theoretical.
We went straight up to 24-bit resolution, like super fancy systems. So we just, all of a sudden, it was just every other month there was something to discover. It was a really exciting time. And now we've reached some stability.
Exciting again.
Oh, yeah.
Iran, I don't know if this is true or not, but it seems to me that if you're going to build a nuclear bomb, you have to test it. And these tests we'll be able to catch.
Yes. This is the main point of the CTVT, that we build a network that works. We already demonstrated that we can pick up just about anything in the world. And so right now
From where?
From anywhere.
Oh.
Yeah, that's the whole thing, right? We built this global network, and we need to ratify it. So it's a political problem. People need to say, okay, we're going to support this and getting into force. But we built the network, and recently, I was in this international meeting, and this high-level diplomat says the scientists have delivered. And, I never thought I heard that, because usually there's no end to this stuff. So we built a network that works. And now we leave it in the hands of our politicians at the international level to get it pushed forward. But yeah, we can detect clandestine nuclear test explosions anywhere in the world.
Are you publishing on this?
We already have. It's all out there. And at this point,
What journals?
Journal Geophysical Research, Geophysical Research International. There's a big community of us now. Before, again, there were 5 cats. Now we're in the hundreds.
Yeah.
So to watch this grow over the last 15 years is like.
You getting grants?
Yep.
Of course, you have to get grants.
Yeah, you have to. That's what we do.
Who would grant for this kind of research?
It varies. Right now, we are working for the National Nuclear Security Agency, and it involves 3D monitoring and also fuel cycle monitoring. And again, this is an application of technology to the betterment of humankind and to preserve the peace and try to keep tabs on nuclear fissile materials and how they're used, and not just for creating power, but also for more nefarious means. And it's a verification system that uses technology as the means to do that. And so this is one of the things we do.
What about the global reach of this research? I heard you, I got from what you said that if it wasn't an active field, say 15 or 20 years ago, it has become active. Does that mean that there are conferences hither and yon, that everywhere in the world people are getting into this kind of science and doing things like you?
Yes. So we have a growing community now. It's a United Nations type effort. So again, all the state signatories of the United Nations participate in this endeavor, and they have access to the data. And so what you're seeing is a lot of capacity development. And a lot of the more established powers already have the technology and the resources, and we're transitioning that to them and developing the capability for it to be done at a higher level than was possible before.
Last question, because we're almost out of time, and that is, it's suggested to me by this last item of how the technology can be used. So it's the incorporation of infrasound into the GEO GEOSS planning strategy.
Yes.
I'm afraid I don't know what GEOSS is, but it seems like this is something that would affect people, going forward in planning and in communities, I'm guessing. And I guess the question I put to you as the last question here today is, how is this going to affect the average person? How is this going to affect our lives, in our cities and our communities going forward, including the GEOSS planning strategy?
The GEOS is a really large-scale thing. It's a geophysical Earth observing system of systems. And so it's very meta, yeah? Okay. So the US is one of the strongest proponents of open data in the world.
Yeah.
And I've been in international meetings at a time when our government was going through a transition stage and a lot of basic services for data have been turned off. And you'd be surprised at the repercussions internationally when people had no access to NOAA, USGS, NASA. A lot of the products that we as taxpayers provide are used globally. And how do we immediately benefit from it? Through basic early warning of natural disasters, of being able to respond decisively during times of crisis. And sometimes you just have to move quickly. The U.S. is very active in humanitarian response. Every time, we have typhoons hitting the Philippines, for example, we mobilize very quickly, the USAID, Department of State, to facilitate these things. And so also happens within the U.S. Katrina not being an example of, hurricane impact and how do we mobilize our forces, and how do we do that efficiently and effectively. The more information you have during times of crisis, the better you can act. So this is where us as citizens can provide additional information that allows the powers that be to make the right decisions and to act promptly.
Okay, so that camera over there, that's the people. That's the people. Those are the people.
Hello, people.
Those are the people with iPhones.
All right.
What do you want to say to them about, contributing their processing power on the iPhones to this effort?
Well, it's a discovery process, and we as scientists can use your help. We need more information, we need more data. So when you're quiescent at night and connected to a Wi-Fi, if you want to contribute to Infrasound, just download the app, push play, and we'll be able to use what you have whenever something happens. Thank you.
Thank you, Milton. Milton Garces, Associate Researcher, Director of the Infrasound Laboratory at the University of Hawaii at NELHA, but it's part of the Hawaii Institute of Geophysics and Planetology. Thank you, Red Butler, for the show in January and for the one today. And thank you. Take care, Milton.
Aloha.
Aloha.